won't show up today like that one.
But they had
No, he's in his office. He gave the main company. He was in his office this morning.
sentence-based, just calculation.
They give you like a problem statement or something.
Yeah, and then, well, I think one of them was like, what's the corrosive, it's like a chemistry question. It's like, what's the corrosive state of steel or something like that? And they had like anoid, cathode, and then a couple other.
Gross.
There's the anoids, so they had to go into the heavy.
Oh, it's just as bad as that uniform.
Oxidation.
And then they got sick.
Rust.
I know that it's steel. It's like those things, those steel cutters that like oxidize it like a super fast rate.
Yeah. Well, some of it was really strange because, I mean, we might have covered it in class, but it was more
They
like
filled
stuff
out
that
even
you know.
Johnson like a week after
Real world
Yeah.
experience.
it came out, and
It's
everybody
kinda
at lunch
strange.
said it was.
You missed last Friday.
Yeah, I haven't even taken steel or concrete. I need to get those classes in.
There was a,
Like, work.
it didn't seem like there was very many scale
No,
questions.
it
If it was mostly like
What's her name?
a question.
Heather Priscilla.
You know, like
So there was a 38 talk or something.
But,
Good morning. Hey. And then Priscilla wanted to. That's all they got. And they got argued, and Heather was the little person, and so she was touching every little thing Priscilla did. She went back there, she pulled the salad out, so she went over to the thing, and just cleaned off. She's like, we go over there and party. She's like, it's got all the black books on all the tables, like your table. She's like, attic. Priscilla was just sitting at the bar waiting to check it.
I mean, it wasn't.
All over.
Very much more.
Priscilla actually.
Well, we need a 60-40.
An extra. Not, didn't miss one.
You know, we have to make it a 60.
So, yeah.
Leverage employees.
She wasn't selling it.
This is why I never.
I mean, it was a story.
Yeah.
Me and Josh used to laugh. It was like Josh. She's still going. It was a good 2 hours.
So how was your report? Funny?
Definitely could be better.
I guess you'll see, won't you? What'd you do this weekend? What did you do this weekend?
The weekend?
Oh.
Why did I do the weekend? Yeah, we had a dinner with some friends.
Oh.
So do like a Halloween?
My kids, yeah, they will.
Did they dress up?
No, not yet.
Not yet. Well, what are they gonna dress up as?
No, they have some, their mothers. Their mother, put on some costume. No, I don't know what.
You'll find out.
Yeah. Okay.
Missing some.
So, good morning, everyone. Hopefully, I'm going to try to finish, a little bit early today because every time I keep you for extra minute or two, so I want to make it up today again. Okay.
All right.
I will try. I'll see if we can finish early. It's just to. I have 2 problems here that we need to solve. If we finish those before the time, then we're going to be good. Okay. So now, what we discussed is how to solve a beam, okay, using the stiffness method. All you have to do is solve that equation, the stiffness equation, P equal KU. That's it, okay? So K is the overall stiffness matrix. We learned how to do this for different structures, okay? if you have an internal hinge, how you can build this K, okay? And also we learned how to deal with the deflection or movement of supports. If you have a movement of support, then that movement at that degree of freedom will not going to be zero. It's going to be that given value, okay? So that when you have a movement of support, that will affect the U vector, the displacement vector, okay? And P is the load vector that comes from the loads, okay? So what we did so far, P is the loads at the degrees of freedom, right? So now, what if you have a load, but it's not at the degree of freedom? What does this mean? Simply, this is the only thing that we didn't discuss so far, okay, is members with intermediate loadings. So let's say you have a member like this, A, B, so the nodes are at the start and the end of that member. A and B are the nodes, okay? If you had a force at those nodes, A and B, you know how to deal with those forces, you just put them in the load vector, okay? But what if you have, from point A and B, you have some load, some uniformly distributed load, triangular distributed load, any load, even a concentrated load in between point A and B, the start and the end of the member. How would you deal with those loads? That's a load that has to be in the load vector, but it's not at the nodes. It's not at point A. It's not at point B, okay? So how would you deal with such a load, okay? That's what we need to learn today, okay? So actually, in the slope deflection method, we learned that there is something called the fixed end moments. The fixed end moments are the reactions, the moment reactions, if the beam is fixed, if there is no rotation or deflection, okay, at the ends. So here, if you have a fixed end moments, those are the fixed, let's say those are the fixed end moments. You have a reaction, a moment reaction, a moment reaction, a vertical reaction here, okay? And those are the fixed end moments, AB, fixed end moment, BA. Those represents what? Those represents the reactions due to that given load, okay? Due to that given load on the member, okay? But according to Newton's third law, what does Newton's third law states? Only 3 laws for Newton. What's Newton's third law?
Every action is equal in opposite reaction.
Exactly. For every action, there is a reaction equal in magnitude and opposite in direction. So now those are the reactions due to this load. What does this mean? That there is an action, the action of this load at those nodes is equal to those reactions in magnitude but opposite in direction, right? So if you have this force, there is an equal and opposite force here that represent the action of that load. If there is a moment here, there is an equal and opposite force that represent the action of that load. An opposite and equal moment, an equal and opposite force here. Okay? So those in red are what? Are the actions. Okay? So what you have to do is you find those fixed end moments or fixed end reactions and find the opposite of them. Okay? Those are the actions that you have to put as a nodal load or a nodal force. Okay? So that's just what you have to do here. Okay? So let's write this. The action of the intermediate loading is equivalent to the opposite of the fixed end. I'm not going to say moments here, I'm just going to say fixed end actions. Why didn't I say fixed end moments? Because here you don't only have moments, you have a moment and a vertical force, for example. Okay, so I'm calling them fixed end actions. Okay, and so how to find those values? Can I borrow your book? No? Okay, no problem, I can. This is yours or hers? So why are we talking? So here, the fixed end moments will be given here, but the vertical forces are not given. But you can find those forces, vertical forces. Do you know how much are the vertical forces here? The actions, sorry. How much do you think they are? P over 2 and P over 2, right? Because this is symmetric, so it's going to be P over 2 and P over 2. For example, here, how much are the vertical forces? The reactions. P and P, right? Due to symmetry, so P, 2P here, so the summation of them are 2P, so you can just add them. How much are the vertical forces here? Yeah, 1.5P here, 1.5P here. Okay, the important one that we always have, uniform load. When you have a uniform load like this, W, how much are those vertical reactions? WL over 2 and WL over 2. So those are the easy ones, okay? What about those cases where it's not symmetric? How much, if this is P, how much are those forces? It's at the distance A and B. Can you find those? Yes, but it's not going to be that straightforward. You have to apply the equations of equilibrium because now you're given the moments here. You just need to find those vertical forces. So you just take the summation of the moments about point A, you're going to be able to find YB here, or BY, and then sigma Fy, you're going to find AY as the difference of P minus BY. Okay? So you can find those vertical forces here, the actions, okay, or the reactions, okay? Any question? Thank you. So you can find those, those fixed end moments are in the table. Those can be found easily, the vertical reactions. And once you find those blue forces, the inverse of them is what you're going to add to your load at the nodes. Okay? Those are going to be the loading at the nodes. Is that the only thing different here if you have an intermediate loading? No. Another thing is when you have an intermediate loading, when you find the reactions then, okay? You remember you have the load vector equal Ku. Out of that load vector, some of the forces are known, okay? And some of the forces are unknown. The unknown forces, usually they are the reactions, right? When you need to find those reactions, okay? You just have to solve this P equal Ku. But now, when you have intermediate loading like this, you have to add those fixed end reactions, okay, to your reactions. Why? Because according to what you learned in the slope deflection equation, okay, if the member is fixed at both ends, the reaction are going to be equal to the fixed end moments, right? But due to the deflection, you have some additional parts. So you have to take the effect of the reaction due to those, intermediate loading and add it to the reactions, okay? So this is the other difference, or the second difference here. And So the first, this is how you build P. And once you build P and you're trying to find the reactions, those actions here. Okay. Sorry. Okay, let me have this here. Once the displacements are found, the fixed and reactions are added to the final calculation, to the final calculated reactions. And here to find the load vector, the actions will be added to the load vector for all contributing members to find the displacements. So the steps that we learned is not different, okay? The only difference here is when you have an intermediate loading, when you try to build the P vector, okay? You just have to add, okay? Or use those fixed end actions, the red ones, okay? To find the load vector. And when you solve for the reactions, you have to add those fixed end reactions to your reactions. That's all, okay? So let's solve two examples here on how we're going to apply this when we have an intermediate loading. We have this beam. It's fixed here, pinned in the roller here. This is point A, B, C. This length is 24 feet from A to B, and then from B to C there is an intermediate load of 12K, and you have 4 feet here and 4 feet here. So from B to C it's 8 feet. And then on member AB there is a uniformly distributed load of 2 kips per foot. For the shown beam, we're required to calculate the moment at point A using the stiffness method. We're given the value of E, the modulus of elasticity. We have 29 times 10 to the power 3 KSI. What modulus of elasticity is this? What material is this? Steel. And I, the moment of inertia of the section of that beam, is 510 inch to the power 4. Okay? So now we just need to solve this problem. How to solve a problem using the stiffness method? What are the steps? I just need to follow the steps that we learned earlier. Okay? What are the steps? What's the first step? Exactly, label my problem, my nodes, my members, my degrees of freedom. Okay? So that's the first step that we're going to do here. That's point A, B, and C. How many members do we have? 3 or 2? Okay. From A to B, that's one member. From B to C, that's the second member. Someone would say, okay, but I have a load here that is equal to 12K right in the middle between B and C. So that's another node, a third node, or you add a third member. So I'll have a member from A to B, and then a member from B to, let's call this node D, for example, and then a member from B to D, and then a member from D to C. What do you think about that? Is that wrong? No, it's not wrong. It's correct, okay? But now you're going to have 3 members, not 2 members, okay? And your degrees of freedom are going to increase, right? You're going to have 2 extra degrees of freedom at point B. So your stiffness matrix is going to be larger. You will need to do more calculations, okay? So when you have intermediate loading just between 2 nodes, you can just deal with that intermediate loading without breaking the member at that node, okay? Definitely, if you break the member at that node, that's fine. That's not wrong, okay? But it will increase the degrees of freedom, and your problem is going to be larger. You will need to do more calculations here, okay? So just 2 members, okay? 3 members it's not wrong, but harder to do. And then how many nodes do we have? We have 1 node here. B is a node, and C is a node. So we have 3 nodes. Do we have any internal hinge here? Is there any internal hinge? No, there is no internal hinge, okay? There is hinge support, but not an internal hinge between 2 members, okay? So that means that if we have 3 nodes, how many degrees of freedom we have, overall degrees of freedom? 6, 2 degrees of freedom at each node, okay? So what are those degrees of freedom? We have a vertical displacement and a rotation, a vertical displacement and a rotation, a vertical displacement and a rotation. So I have those 6 degrees of freedom. What I need to do is I need to label those degrees of freedom. You can label them whatever you want, but we said what's the easiest way to label them?
Unknowns first.
Unknowns first. What are the unknown degrees of freedom out of those 6 degrees of freedom? Let's see here. The vertical displacement. Is the vertical displacement here, or here, or here? Known or unknown? How do you know if a degree of freedom is known or unknown? What makes your degree of freedom known or unknown? The support, okay? If there is a support that prevents that motion, okay? Do you have a support here that prevents the vertical motion? Yes, so that means that this one is known, it's 0. Do you have a support here that prevents the vertical motion? Yes, so the vertical displacement here is 0, it's known. Do you have a support here that prevents the vertical motion? Yes, so this vertical displacement is 0. It's known. What about the rotation? Do you have a support here that prevents point A from rotating? Yes, it's a fixed support. So this angle of rotation is 0 due to the fixed support. Do you have the support here that prevents the point from rotation? No, this bent support or a roller support, they don't prevent or they don't constrain the rotation. Okay? This rotation is allowed. The beam member here can rotate. So this one, the rotation here is unknown. You don't have anything that is constraining the rotation here. What about this point? Is there any type of support that is constraining the rotation here? No, so this rotation is unknown. So this rotation and this rotation are unknown. So I need to start labeling them first. So this is what I'm doing here, 1 and 2. Okay? And then the rest of the degrees of freedom, I can label them freely, any sequence. This is the sequence that we chose here, 3, 4, 5, and 6. So I have those 6 degrees of freedom, okay? So that's the first step here. Step 1, the notation. I have 2 members. What does it mean that I have 2 members? It means that I will need to build 2 members, stiffness matrices. A K for member 1 and a K for member 2. Okay? If If I have 3 members, then I have to build 3-member stiffness matrix, okay? And I have 3 nodes. None of them is an internal hinge. That means that I have 6 degrees of freedom. Those 6 degrees of freedom, some of them are unknown and some are known. What are the unknown degrees of freedom? The first, the second are the unknown degrees of freedom. The first represents what? It represents the rotation at point C. The second one represents the rotation at point B. So those are the unknown degrees of freedom. And then I have the rest, the third, the fourth, the fifth, the sixth degrees of freedom are known. The third one is the rotation at point A. The fourth one is the deflection at point A. The fifth one is the deflection at point B. The sixth one is the deflection at point C. And all of those are 0 because of the supports. So those are known degrees of freedom. That's the first step, the notation. I have all my members, nodes, and degrees of freedom labeled. Okay? What's the second step? What's the second step? Build the member stiffness matrix for each member I have. So here, member stiffness matrices. I have K is equal to EI. You don't have to memorize this, but you have to memorize how it's arranged. Okay? It's 12 divided by L cubed, 6 divided by L squared, negative 12 divided by L cubed, 6 divided by L squared. That's equal to the first column as well. And then the second row is 4 divided by L, negative 6 divided by L cubed, 2 divided by L, negative 6 divided by L cubed, 2 divided by L, 12 divided by L cubed, negative 6 divided by L squared, negative 6 divided by L squared, 4 divided by L. Definitely don't have to memorize this. When I was student, I memorized it, okay? But now I'm an old man, you know, I don't memorize it, okay? But I know maybe you don't want to memorize it now, so you're going to be given this on the test. But you have to memorize and know the arrangement. What does those numbers represent? Okay? Each one, you start with delta and theta at the near end and delta and theta at the far end. That's the only thing that you have to memorize. It's arranged as follows. Delta and theta, not theta and delta. Delta and theta at the near end, and then delta and theta at the far end. Okay? So for K1, to find for K1, how much is L? How much is the length of member 1? 24 feet. So, and how much is EI? E is 29 times 10 to the power 3 KSI. This is 24 feet. And I was 500, right? 510 inches per 4. So when you build this stiffness matrix, can you use those units? No, why not? They are not consistent. The loads are in kips, and here the dimensions are in inch per 4, but the length here is in foot. So what you have to do is you just have to multiply here to have consistent units. Just multiply this by 12 inch per foot to have everything in inches. So the units are in kips and inch, okay? and substitute this for K1. So therefore, K1 is equal to, those are the numbers that you're going to get by substituting those numbers. 7.43, 1069.9, negative 7.43, 1069.9, and that's the equal to the first column as well. And then the second row, 205,417, negative 1069.9. That's equal to the second column. Then the third row here, we have 7.43, negative 1069.9. Always check that your matrix is symmetric, okay? Each and every matrix that you're going to have has to be symmetric, okay? Stiffness matrix for the element, the stiffness matrix, the overall stiffness matrix for the entire structure, each one of those has to be symmetric. So that's K1. Now I need to label this K1, those numbers. What degrees of freedom are they relating to each other? Those numbers here. What degrees of freedom do you have here for that element 1? You have to memorize this. It's delta and theta at the near end and delta and theta at the far end. So that's delta and theta at the near end, so 4, 3. And delta and theta at the far end, 5 and 2. So 4, 3, 5, and 2. 4, 3, 5, and 2. 4, 3, 5, and 2. Okay? And then, so here, units are in kips and inch. Okay? Now I just need to build K2. Would it be the same numbers for K2? Why not?
8 feet.
The length is different. So L, so for K2 here, L is equal to 8 feet multiplied by 12 inch per foot. So it's 96 inches. So K, the values for K is going to be different. Okay? Just substitute the same, formula, the same stiffness matrix, but the values are going to be different because the length is different. You're going to have those values. 9628.91, negative 200.602, 9628.91, 9628.91, 616250. I'm sorry. Negative 200.602, 9628.91, 616250, negative 9628.91, 3081.25. I guess your calculators, you can program them, right? You can save, you can have those parameters and save values, like you can save 12EI divided by L cubed, right? And you just enter E, I, and L, and then it calculates that element for you, right? Your calculator can do this, right? My time, when I was a student, My calculator was just adding, subtracting, doing multiplications, calculating cosine and sine. But I guess your calculators nowadays, they are really good. You can just have saved this matrix, okay? In terms of those parameters, E, I, and L, okay? And you just substitute the value of E and I and L, and then it's going to substitute those values and give you the numbers right away. I'm not sure you would know your calculator more than I do, okay? If your calculator cannot do that, then you just, do the calculations, 12EI divided by L cubed, or 6EI divided by L squared, or 4EI divided by L. You see here those values, okay? They are not all different. All you have is 12 divided by L cubed, 6 divided by L squared, 4 divided by L, and 2 divided by L. Those are the values that you have here. Okay? And then everything else is the same, either with a positive sign or a negative sign. So it's just 4 elements, and then it repeats itself either with a positive or a negative sign. So here you have 200.602, negative 9628.91, negative 9628.91, 616250, and that's the K2, the stiffness matrix for element 2. What you need to do is label it now. What are the degrees of freedom for that element? 5, 2, 6, 1. Okay? 5, 2, 6, 1. Delta and then theta, delta and then theta at the near and then far end. Okay? 5, 2, 6, 1. Five, 2, 6, 1. 5, 2, 6, 1. Anything left for step 2? Step 2 is building each element stiffness matrix. Yes?
The 6.
That's the value that I have here, 206.02. Why are you're saying it should be how much?
1, 2. 6,
What?
6 should be 1, 2.
This one should be equal to this one? 1 to this one? Why? Those are two different values. Here you have 6 divided by L squared, here you have 12 divided by L cubed. Right? All you need to have here is that the first row is equal to the first column, symmetric. Second row is equal to the second column. The third row is equal to the third column. The first row is equal to the first column. The fourth row, is equal to the fourth column. Okay? So that's K1 and K2. What's the next step?
Overall.
Find the overall stiffness matrix. Overall stiffness matrix. So K, how big K is going to be? How big it's going to be? 6 by 6. You have 6 degrees of freedom, so it's going to be 6 by 6. So K is 6 by 6. One, 2, 3, 4, 5, 6. Okay? Let's just put this here. So right now, okay, this is the first time I'm going to do this with you. Do I need to find all those 36 elements? 6 by 6, you have 36 elements. What do you need to find? After building this, you're going to do what? Subdivide it, right? Where are you going to subdivide it? You have here 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. You're going to subdivide it into 4 different submatrices. where you're going to do this subdivision. Add the 2, right? Why? Because only the first two unknowns are first two degrees of freedom are unknowns. So I'm just going to subdivide it here. Here. So which element should I find? I need those elements here, those 4 elements, to find the displacements, and I need those elements to find the actions. Okay? That's all I need. So instead of finding the 36 elements, okay, I'll just find 12 elements. Okay? This part here is not needed. I don't need to find this part of the matrix. Okay? It's not 0. It's just not needed. If you put it 0 on the test, I'll give you 0. Okay? Because it's not 0. Okay? There are numbers there, but you just don't need them in your calculations. So now let's build this part here. This is what we need here. 1 and 1. Where do you have 1 and 1? You have 1 and 1 here. So 616, 250. Okay? Is there 1 and 1 in K1? No. So it's just that element. 616, 250. 1 and 2. There is 1 and 2 here. 1 and 2. So 30, 81, 25. 30, 81, 25, and it's symmetric, so it's equal to that element. 1 and 2 is equal to K2 and 1. And then 2 and 2. Is there 2 and 2 here? Yes, there is 2 and 2 here. It's this element. And there is 2 and 2 here. It's this element. So you just have to add them together. Okay? So K2 and 2 will be 82, 1667. Okay? And then I need to build those numbers here. 1 and 3. Okay? 1 and 3. Is there 1 and 3 here? No. There is no 1 and 3 here. 1 and 3. Is there 1 and 3 here? No. So that's 0. So it's 0 here. And then 3 and 2. 2 and 3. Doesn't matter which one comes first. 2 and 3 or 3 and 2. 2 and 3. Is there 2 and 3 here? No. Is there 2 and 3 here? Yes. 2 and 3. So 102, 708. Is it symmetric? We just copy this here? No, definitely not, because this one is 2 and 3. It's equal to 2 and 3 here. It's equal to this element. This one is equal to this. Okay? So just be careful. And then 1 and 4. 1 and 4. Is there 1 and 4 here? No. Is there 1 and 4 here? No. So it's 0. And then 2 and 4. Building 2 and 4. 2, there is no 2 and 4 here. There is 2 and 4 here. It's that element, 1069.9. And then 1 and 5. There is 1 and 5 here, 96 to 28. And there is no 1 and 5 there. So 96, 28. And then 2 and 5. Let's see here, 2 and 5, and 2 and 5. So you just have to add those terms together. Have 2 and 5 here, negative 1069.9. And 2 and 5 here, I have 9628. Add them together. You're going to have 8559.01. And then 1 and 6, I have 1 and 6 here. And there is no 1 and 6 up in K1, so it's negative 9628.91. Negative 9628.91. And then 2 and 6, 2 and 6. There is no 2 and 6 in K1. There is 2 and 6 here. It's negative 9628.91 as well. So negative 9628.91. Nothing new. So far, there is nothing new. Okay? So that's step 3. We build the overall stiffness matrix. Okay? What's next? What's step 4? What do you need to do next? Okay, so build P, the load vector, and the displacement vector U. P and U. U is not the problem here, okay? U is what? U is going to be 6 by 1. The first two are the unknown degrees of freedom, which are theta C and theta B. And then the unknowns, the rest are unknowns. This is U. Those are known, and those are unknown. Sorry, the opposite. Those are unknown, and those are known. They are zeros. Now we need to build P. How big is B? P, it's 6 by 1. Okay? How to build P? P is the forces at those degrees, or the loads at those degrees of freedom. What are you going to have here? You're going to have the first two being known, and the last two being unknown. Okay? Any question here? So how to build those? Those unknowns are the forces at those degrees of freedom. Those are 1, 2, 3, 4, 5, 6. Are those the reactions? No. Those unknown forces are not the reactions. They are the reactions if you don't have intermediate loading. But if you have intermediate loading, they are not the reactions. You just have to add the fixed end reactions to find the intermediate reactions. So I'm just going to call them P3, P4, P5, and P6. Okay? Now I just need to find those values here, because those should be known. Okay? What are the forces at those degrees of freedom, the first and the second degree of freedom? Where are the first and second degree of freedom? It's the moment here. This is the first degree of freedom. So how much is the moment here? And how much is the moment here at the second degree of freedom? That's the new thing that we have here. Is there a direct moment? Is there a moment here? Can you see a moment here? No. But there is a moment here that comes from what? Comes from this intermediate load. This intermediate load has an equivalent moment and force at the end. Okay? This intermediate load has an equivalent moment and forces at the end. Okay? That's what we need to find now. Okay? So here, to find this P, okay, I have member 1 like this. How much is the length? It's 24 feet. It had a uniform load. This is member 1. It had a uniform load of how much? 2 kibs per foot. Okay? This load is equivalent to a moment here, and the moment here, and the force here, and the force here. You have to be careful with the direction. How do I know those directions? They are the opposite of the fixed end moments. How do you find the direction of the fixed end moments? They are at the back of your book, the table at the back of your book. Right? how much are those fixed end moments? Just look at the back of your book. How much are those fixed end moments? WL squared divided by 12. So W is 2 kips per foot. L is 24 feet squared divided by 12. So that is equal to 96 kips feet. But you just remember that we're using what units are we using here in this problem? We're using kips inch, so I just have to multiply this by 12. So it's 1152 kips inch. And it's the same value here, 1152 kips inch. Now, what are the signs of those moments? What method are we using? Are we using the slope deflection method or the stiffness method? Stiffness method. What's the sign rule for the stiffness method? For the moments, if they are counterclockwise, that's positive. If they are clockwise, that's negative. So this one is clockwise, so that's negative. The other one is counterclockwise, so that's positive. Okay? How much are those vertical forces? WL divided by 2. How much is W? It's 2 kips per foot multiplied by the length, which is 24 divided by 2. So that's 24 kips. And here you have 24K. What's the sign? Those 24 kips. It's going downwards. Is it positive or negative? The sign rule for the stiffness method is upward is positive, downward is negative. That's it. So this is negative, this is negative. Okay? So those are the forces here. For the other member, this is member A, B. For the second member that starts at B and ends at C, you have a force here that is equal to 12K. The length of the member is 8 feet. This load is right in the middle. So this load is equivalent to nodal forces here. Some forces at the node. How much are the vertical forces? 6K and 6K. It's going downwards, so they are negative. What about those moments? How much are those moments? It's from the back of your book. Okay? PL over 8. So PL over 8. P is 12K. L is 8 feet divided by 8. So you have 12 kips feet. Multiply this by 12, so 144 kips inch. And this one is 144 kips inch as well. The sign, this one is clockwise, so it's negative. And this one is counterclockwise, so it's positive. So now, when I ask you, how much is the moment that is applied at the third degree of freedom? Where is the third degree of freedom? Sorry, the first degree of freedom. What's the first degree of freedom? Just look at the labeling when you labeled your problem. What was the first degree of freedom? The rotation at point C. So how much is the force at the point C here? The rotational force, the moment at point C. 144 kips inch. So that's what I have here. What about the second degree of freedom? What's the second degree of freedom? The rotation at B. What moment do you have at point B? You have two of them. There is a moment here at point B from member AB, and there is a moment here at point B from member BC. Which one would you use? Both. Add them together. Okay, so you add the action that comes from both members. So I'm going to add the 1152 plus the second one, which is negative 144. So now that's the load vector. Okay? So that's the new part that we had here. When you have intermediate loading, how to build the load vector, you have to find the equivalent action for those intermediate loading. How to find that? It's so simple. The moments are equal to the opposite of the fixed end moment, and those vertical forces, if it's symmetric, it's just you're going to divide the load by 2. If it's not, then you have to use the equations of equilibrium to find how much is the vertical reactions. Okay? Any question? Okay, what's the next step? This is step 4. What's the next step? Step 5. Write the equation. Write the stiffness equation. What does the stiffness equation look like? P equals KU. Okay? So it's so simple, I'm not going to write it here because it's just P, this P, equals to that K multiplied by that U. Okay? When you write this, you need first to solve the first two equations, okay, to find the displacements. So solve the first two equations. You're going to find that displacements, the unknown displacement, theta C is going to be negative 0.4673 times 10 to the power negative 3 radian, and theta B is going to be 1.40203 times 10 to the power negative 3 radian. And then what? You need to find the reactions, right? How do you find the reaction? By substituting those values into the last four equations, right? But substituting that into the last four equations will give you those forces P3, P4, P5, and P6. Those are not the reactions. The reactions are those forces P3, P4, P5, and P6 plus the fixed end reactions at those nodes. Okay? So let's see this here. So substitute into the last four equations and add the fixed end reactions to find the reactions. So let's see here, what do I mean by this? P1, P2, P3, P3, P4, B5, B6 comes from the substitution, okay, of the stiffness matrix multiplied by the load vector. Multiplied by theta C, which is negative 0.4673 times 10 to the power negative 3 radian, and theta B, which is 1.40203 times 10 to the power negative 3 radian. Okay? It's just the row times the column. The first two values by the first two values, which are theta C and theta B. Okay? That doesn't give you the reaction. That gives you P1 or P4 to P3 to B6. And then the reactions let's see here. The reactions. What's the reaction at the third degree of freedom? The third, the fourth, the fifth, and the sixth degree of freedom. What are the names of those reactions? What is the name of that reaction at the third degree of freedom? MA. That's the reaction, MA. The fourth degree of freedom, AY. The fifth is BY. The sixth is CY. Okay? So those are the reactions here. MA, AY, BY, CY. So the reactions MA, AY, BY, CY are equal to P3, P4, P5, P6 plus a vector that has the fixed end reactions. The first vector here, P3, P4, P5, and P6 comes from here. Multiply this by this, give you P3. This by this is going to give you P4. This by this is going to give you P5. This row by this column is going to give you P6. Okay? So those are known here. Those are equal to 144 Gibbs inch. It's moment, so it's in Gibbs inch. This is a force, so it's 1.5 Gibbs. This is a force, it's 7.5 K. This one is negative 9 K. And the fixed end reactions. How much are the fixed end reactions at those degrees of freedom? The third, the fourth, the fifth, and the sixth. The third is what? It's the moment here. It's 11:52. But that was the action. Here I'm calculating the reaction. So how much is the reaction? It's the same value, 11:52, but it's positive, not negative. Okay? So 11:52. Gibbs inch. P4. How much is P4? The reaction at the fourth degree of freedom. It's this one. But this one is the action. It's negative 24. How much is the reaction? Positive 24. Okay? $24K. The third degree of freedom. Sorry, the fourth degree of freedom. The fourth degree of freedom is the vertical reaction at point B. How much is this? You have here negative 24. You have here negative 6. So it's negative 30. All you have to do is just reverse the sign. It's 30, not negative 30. I guess I have something wrong here. Negative 6 and 24. Yeah, okay, that's correct. And then for the 6th degree of freedom, it's this one. You have negative 6 here, so what do you put in your reaction? It's 6, not negative 6. You add those together. So previously, in our previous problems, when we didn't have intermediate load, those were the reactions. All I did now is just added the fixed end reactions to them. Okay? So that's equal to 108 Gibbs feet by dividing by 12, and then 25.5 K, and then 37.5 K, and negative 3 K. Those are the reactions. Only two differences. How you built the load vector was different. Okay? You needed to find those forces to build the load vector. And how you found the reactions, it's exactly the same, but you just needed to add the fixed end reactions to your calculation. This is how you deal with intermediate loading. Any question? Okay. Let's see another example here. In this example, we have a beam A, B. And in this beam, there is a load P right in the middle. How much is P? It's just P. Just leave it as P, okay? We need to find everything in terms of that load P. The length is 2 meters and 2 meters, okay? And we're required here to find the deflection at point A and the reactions. So here, something new here. What type of support do we have at point B? Fixed. What support is this? This notation, it might be new for you. This is not a roller. This is not a pin. This is not a fixed support. It's a slider support. It's a support that prevents the rotation, but it doesn't prevent the vertical motion. So the rotation is 0. There is no rotation. It's like the fixed support, but it allows vertical displacement. Okay? So the support at point A is a slider support. That means that theta A is constrained, it's equal to 0, but delta A is unknown. Okay? The displacement is not constrained. Okay, now we need to solve this. How would we solve it? What are the steps? Step 1, the notations. How many members do we have? Just one. Okay? How many nodes do we have? 2. If we have 2 nodes, do we have any internal hinge? No. That means that how many degrees of freedom that we have? 4. Vertical displacement, a rotation, a vertical displacement, and a rotation. Okay? Those are the 4 degrees of freedom. Let's label those degrees of freedom. The unknown degrees of freedom first. Those two degrees of freedom here, the vertical displacement and the rotation, are they known or unknown? It's fixed, so the deflection, the rotation point B is 0. Here, the vertical displacement, is it known or unknown? Unknown. The rotation, it's known, it's 0. So the only unknown here is delta A, this 1. So I'm just going to label it 1, and then I'm going to unlabel, I'm going to label the unknown degree, the known degrees of freedom 2, 3, and 4. So here we just have one member, 2 nodes, and 4 degrees of freedom. Out of those 4 degrees of freedom, the first one represents delta A, okay? This is unknown. And the second, the third, and the fourth, the second represents theta A, the third represents delta B, the fourth represents theta B, and those are all zeros. So those are known. That's the first step. What's step 2? Build the member stiffness matrix. How many member do we have here? Just one member. So it's just K. You're just going to have K1. Which is, you have it, 12EI divided by L cubed, and so on, right? And then the step after building this, okay, is what? Build the overall stiffness matrix, right? What's going to be the overall stiffness matrix? K1, because you just have that member. So K1 is equal to K, okay? This is the overall stiffness matrix. So the overall stiffness matrix is going to be 4 by 4, okay? So it's like this. And then this overall stiffness matrix, what do you have to do? You have to subdivide it into the unknown part and the known part, right? You have 1, 2, 3, 4. 1, 2, 3, 4. You have to subdivide it. Where will you subdivide it? So you're going to subdivide it here. Which part you need to find? You have 4 submatrices. This part is not needed. You just need this part. So all you need to find is just those 4 elements. So the first one here, if we have EI here as a common factor, it's 12 EI divided by L cubed, so 0.1875. And then this one is 0.375. This one is negative 0.1875. This one is 0.375. That's all I need to find. These 3 elements are equal to those 3 elements, okay? This is K. So that's actually step 2 and 3. Because K1 is K, right? This is the overall stiffness matrix. What's step 4? Build U and P. U, we already know that's what's U, the unknown degree of freedom. We have delta A, and then the rest are zeros. That's U. What about P? P, the load vector, is going to be subdivided. The first value is known, and then the third 3 are unknowns. P2, P3, P4. Why didn't I write the reactions? Because they are not equal to the reactions. Okay? What's the first value here? How can I find it? So I only have one member, right? On that member, I have a load here, P, and the length is 4 meters. I need to find the equivalent end forces to this force. How much are those? How much are those forces, equivalent forces? P divided by 2, P divided by 2. And there are moments here. How much are those moments? From the back of your book, just find the fixed end moments and put the opposite of it. PL over 8. P is P, L is 4, divided by 8. So it's P divided by 2. And here you have P divided by 2. What are the signs? This one is clockwise, so it's negative. This one is counterclockwise, so it's positive. So how much is the force here at the first degree of freedom? That's the first degree of freedom, right? How much is that then? Why negative? Because this is going downwards, so it's negative, right? So that's the load vector. Okay? So now, what's the next step? build the stiffness equation. P equal KU. P equals K U. How much is delta A then? Negative P divided by 2 is equal to EI 0.1875 multiplied by delta A. That's the first equation, right? That's what the first equation says. The first equation says that negative P over 2 is equal to EI multiplied by 0.1875 multiplied by delta A. So therefore, delta A is equal to negative 2.67 P divided by EI. That's the first thing that you were required to find. How much is delta A? It says it's a function of P. And then you need to find the reactions. How would you find the reactions? It's those P2, P3, and P4, but you have to add the fixed end reactions to them. The reactions, they are MA, YB, and MB. They are equal to that vector EI multiplied by 0.375, negative 0.1875, 0.375, multiplied by that delta B, which is negative 2.675 P divided by EI, plus the fixed end reactions. What are the fixed end reactions? At the first degree, at the second degree of freedom, this one, it's negative P over 2, so just the opposite, P over 2. And then the third degree of freedom, I have negative P over 2, so it's going to be P over 2. And then negative P over 2 is going to be, sorry, positive P over 2, it's going to be negative P over 2. So P over 2 and negative P over 2. So you do this, it's going to be negative P over 2, P, and negative 1.5 P. Those are the reactions. So that's the difference. I just need to edit this part. Any question? Okay, so thank you. Sorry I wasn't able to make you leave early, but at least it's 10:45.
What design project?
Foundations.
Yes.
No, we're good.